Hello there, and welcome to the calm cosmos. I'm so glad you're here. Tonight, we're going to drift gently through the swirling skies above us as we unravel the secrets of weather. Those soft breezes, rolling thunderheads, delicate snowfalls, and sun-warmed afternoons that make up the ever-changing mood of the sky. Think of this as your invitation to float weightlessly through the clouds, all while staying tucked up and cozy wherever you are. Now, I should give you a gentle warning. While this video is designed to help you unwind and ease into rest, there's always the small risk that it might be just interesting enough to keep you listening. But if you do end up wide-eyed at 2 a.m. thinking about cumulonimbus clouds and the Coriolis effect, well, at least you'll be a little smarter for it. Before we begin, I'd love to know where in the world are you watching from and what time is it for you right now. Whether you're tuning in at midnight dawn or somewhere in between, it's lovely to have you here. If you enjoy relaxing, curiosity-filled journeys like this one, please consider giving this video a like and subscribing to the channel. It helps the Sleepy Scientist grow, and it means more people like you can drift off with a head full of gentle wonder. And just a quick reminder, while we'll talk about temperature, pressure, and a few things that may relate to how your body responds to weather, this video is for educational and entertainment purposes only. It's not intended as medical advice or substitute for professional care. If you have any health concerns, especially relating to heat or cold, please consult a qualified medical professional. So, close your eyes if you like, let your shoulders drop, and take a long, slow breath. Tonight, we're going to explore how weather works, the science behind every raindrop, rainbow, and rumble in the sky. Let's begin. Let's start by looking at something that surrounds us all the time, but is often overlooked, unless it's misbehaving, of course, the air. We live at the bottom of an invisible ocean of gases, a vast and gently swaying sea we call the atmosphere. Unlike the ocean of water, we don't need a snorkel to breathe in this one, though it can occasionally make your hair do strange things and your paper fly off the table. The atmosphere is the stage upon which all weather plays out. It's about as thick, proportionally, as the skin on an apple. Most of it hugs the earth in a tight, shallow band. If you've ever been on a plane and looked out the window while cruising at 35,000 FT, you've already risen above a good chunk of it. The atmosphere is made of layers, each one with its own personality, like the strata in a cake, but a lot less tasty. The lowest layer, where all the weather we care about actually happens, is called the troposphere. It's where clouds form, rain falls and wind gets up to all sorts of mischief. The troposphere stretches up to about 7 mi high on average, though it can be taller near the equator and shorter near the poles. Above that we move into the stratosphere, which is where you'll find the ozone layer, Earth's very own pair of sunglasses, shielding us from the sun's more mischievous rays. Keep climbing and you'll pass through the mesosphere, where meteors burn up in bright streaks. Higher still is the thermosphere, a realm of auroras and satellites, where temperatures can reach thousands of degrees Fahrenheit, but it wouldn't feel hot because the air is far too thin to conduct heat. At the very edge, merging with space, is the exosphere. This is the whispery fringe of our atmosphere, where molecules are few and far between and tend to drift off into the cosmic beyond. But for now, let's stay cozy down in the troposphere, our home layer. The air here is made mostly of nitrogen, which makes up about 78% of the mix. Oxygen takes up around 21%. The rest is a cocktail of trace gases like argon, carbon dioxide, and a dash of water vapour, depending on where you are. It's not the most glamorous blend, but it's perfect for life as we know it. Now, let's talk about how air behaves, because this is where things start to get interesting and a little squiggly. Air is a fluid, just like water. It flows, it swirls, it tumbles, and crucially it reacts to changes in temperature and pressure. Warm air tends to rise because it's less dense. Cold air sinks because it's heavier. This simple principle, warm air up, cold air down, is the heartbeat of weather. When the sun shines on the Earth, it doesn't heat everything evenly. The equator gets a lot of sunlight, while the poles get very little. Land warms faster than water, mountains are colder than valleys. All these differences create uneven heating, which causes pockets of warm and cold air. And because nature absolutely loves balance, the atmosphere is always trying to even things out. Let's imagine a nice sunny patch of ground. As the sun warms it up, the air above that spot begins to rise. As it rises, it cools. Cooler air can't hold as much moisture, so if there's water vapour in that rising air, it condenses into tiny droplets, forming clouds. Meanwhile, the surrounding cooler air rushes in to take its place. This movement is called convection. It's the same principle that helps cook a roast dinner or move bubbles through a pot of boiling soup, just on a much, much bigger scale. Now, about pressure. Air has weight. Not much, but enough that the weight of all the air stacked above you adds up to around 14 pounds per square inch at sea level. That's like having a small cat gently pressing on every inch of your body at once. We call this atmospheric pressure, and it changes depending on your altitude and on the weather. High-pressure systems are like lazy weather. They're stable, calm, and often bring clear skies. Air is gently sinking, which discourages clouds from forming. Low-pressure systems, on the other hand, are far more lively. Air is rising, encouraging clouds to grow and often leading to rain or storms. The difference in pressure between two areas creates wind. As air moves from high to low pressure in an attempt to equalize things, it's a bit like atmospheric tidying, though with a lot more mess involved. And because the Earth is spinning fast in fact, at over 1000 Hwm at the equator, this movement of air gets twisted and turned. This twisting is called the Coriolis effect, and it means that winds curve as they travel. In the northern hemisphere they curve to the right, in the southern hemisphere to the left. It's one of those delightful scientific quirks that sounds like magic, but is really just physics doing its thing. Add in moisture, topography, and time of day, and you've got a recipe for constant motion. The atmosphere is always shifting, always flowing. It's never the same from one moment to the next. Even on a calm, cloudless day, there are quiet currents of air slipping past you, subtle changes in humidity, invisible dances of temperature gradients. It's a system that's not just alive, it's lively. What's truly elegant is that this whole swirling, ever-changing engine runs without a single switch or command. It is self-organizing, driven by physics, gravity, and the golden rule of thermodynamics. Energy tends to spread out. Heat wants to move from hot places to cold ones. Pressure wants to equalize. Water wants to evaporate and then fall and then evaporate again. And the atmosphere, it wants balance. It rarely achieves it, of course, but it never stops trying, and that's why we have weather. Because Earth is a restless sphere wrapped in warm gases, dancing with sunlight and spinning through space. Every gust of wind, every cloud, every raindrop is part of this continuous quest for equilibrium. So, next time you look up and see clouds scuttling across the sky, or feel a breeze ruffle your hair, you'll know those aren't just random movements. They're part of something vast and beautiful. An ancient invisible ballet choreographed by sunlight and stirred by gravity. And it all begins right here in the air we breathe. The sun may be about 93 million miles away, but it's the ultimate puppeteer of our planet's weather. Without it, Earth would be a cold, dark rock with no wind, no clouds, and certainly no weather apps warning us about scattered showers that somehow drench our socks completely. The sun's energy is the single largest driver of all weather. It arrives in the form of sunlight, technically electromagnetic radiation, which warms the Earth's surface. But here's the first twist. The sun doesn't heat the atmosphere directly. Instead, it heats the ground, the oceans, and everything resting on the planet's surface. These surfaces, in turn, heat the air above them. So it's not sunshine warming the air directly. It's the Earth radiating warmth back upwards, a bit like a stovetop heating the air above it after being turned on. Now, not all parts of the Earth absorb sunlight equally. Thanks to the planet's shape and tilt, some regions get a generous solar spotlight, while others have to make do with a dimmer glow. The equator, for example, receives sunlight more directly than the poles. This leads to a delightful and persistent imbalance. The tropics warm up quickly while the polar regions remain chilled. And when there's an imbalance, nature does what it always does. It tries to smooth things out. The result is motion, constant, beautiful atmospheric motion. Warm air near the equator rises. As it does, it creates an area of lower pressure near the surface. Air from higher pressure regions flows in to fill the gap. Meanwhile, the rising air moves aloft and eventually travels toward the poles, cooling as it goes. At higher latitudes, the air descends and starts moving back toward the equator near the surface. This large-scale circulation is known as a convection cell. But because the Earth is large and round, and we humans love to name things, we've identified three main convection cells in each hemisphere. Nearest to the equator is the Hadley cell. Above that, in the mid-latitudes, lies the Ferrel cell, and near the poles there's the polar cell. Together these cells help redistribute heat from the equator toward the poles and keep the atmosphere circulating like a giant invisible conveyor belt. Within these cells we find major wind systems. Near the equator, for instance, there are the trade winds, reliable easterly winds that blow from east to west. Sailors have used these winds for centuries to cross oceans, sometimes unintentionally. If you've ever wondered how people accidentally discovered new continents, trade winds are a big part of the answer. Moving a little farther from the equator in the mid-latitudes, we find the westerlies, winds that blow from the west toward the east. These are the ones responsible for pushing weather systems across North America and Europe. And farther poleward, we encounter the polar easterlies, cold, dry winds that blow from east to west near the Arctic and Antarctic. Now, these wind patterns would travel in straight lines if the Earth weren't rotating. But here comes the next twist in our weather tale, the Coriolis effect. Because the Earth spins, anything moving over its surface, including air, gets subtly nudged off course. This isn't because the air has feelings or stage fright, but because of physics. Picture this. The Earth rotates fastest at the equator and more slowly near the poles. If air moves from one latitude to another, it brings along its rotational speed. This mismatch causes it to deflect. In the northern hemisphere, it curves to the right. In the southern hemisphere, to the left. The Coriolis effect doesn't make air spiral like a toilet flush. It's not that dramatic. But over long distances and timescales, it has a profound effect on wind patterns. It's why cyclones spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere, and it's why global wind systems form those neat consistent bands rather than chaotic spaghetti-eek messes. If you zoom even farther out, you'll find another powerful influence on our weather, the jet stream. Jet streams are narrow bands of fast-moving air snaking their way high above us, at the boundary between major air masses. The most well-known one is the polar jet stream, which flows between the cold polar air and the warmer air of the mid-latitudes. It typically sits around 6 to 9 meters above the surface and can reach speeds over 200 mph. That's faster than most sports cars, though thankfully with fewer tailgaters. Jet streams form where there are strong temperature contrasts in the atmosphere. Think of them as rivers of wind steering weather systems across continents. When a jet stream dips or rises, it can bring cold snaps or heat waves, influence storm development, and make weather forecasters either very happy or extremely nervous. They also affect your flights. If you've ever flown from west to east and noticed your journey was shorter than the return trip, you've likely caught a ride on the jet stream. It's the atmospheric equivalent of a moving sidewalk, only much, much faster. But the Earth isn't just spinning and warming and jet streaming. It's also tilted by about 23 test-rulers to be precise. This tilt is what gives us seasons. As the Earth orbits the Sun over the course of a year, different parts of the planet receive different amounts of sunlight. When the northern hemisphere is tilted toward the Sun, it experiences summer. The days are longer, and the Sun is higher in the sky, delivering more concentrated energy. Meanwhile, the southern hemisphere is tilted away, experiencing winter. 6 months later, the roles reverse, and during the in-between times, spring and autumn, both hemispheres receive roughly equal sunlight. This shifting sunlight pattern changes temperature distributions across the globe, which affects wind patterns, storm tracks, and the behavior of oceans. Speaking of oceans, those vast blue basins covering over 70% of the Earth's surface, they're not just passive players, they absorb huge amounts of solar energy and store it like thermal batteries. Water takes longer to heat up than land, but it also cools down more slowly. This difference in heating and cooling between land and sea is one reason coastal regions have milder climates. Oceans also move. Giant currents like the Gulf Stream or the Croyo current transport warm water across great distances, helping regulate the climate. And when ocean conditions shift significantly, like during El Niño or La Niña events, they can have global ripple effects on rainfall, droughts, and temperatures. So, to recap, without ever needing to get out of your cozy bed, you've now floated through the complex choreography of Earth's weather engine. The sun heats the planet unevenly. That heating causes air to rise and fall. The spinning Earth deflects this air into graceful curves. Jet streams carry it across the sky like high-speed ribbons, and the tilt of our planet ensures that no part of the Earth ever stays exactly the same for long. The result? A planet where no 2 days are ever truly alike. Where the wind you feel on your cheek the clouds drifting lazily above, and even the pattern of rain on your window are all part of a grand planetary ballet powered by sunlight and shaped by motion. It's a delicate balance, one that's been playing out for billions of years, and all of it, from the smallest breeze to the fiercest storm, begins with the sun's warm and distant touch. Moisture in the air is one of those things you don't usually notice until it's either making your hair misbehave or fogging up your glasses. But the truth is, the invisible water drifting through the atmosphere plays a central role in shaping weather across the planet. It creates clouds, causes rain and snow, and fuels storms. It's also responsible for some of the most beautiful and dramatic scenes in the sky. In short, moisture is the atmosphere's secret ingredient, and it's everywhere, even when the skies look perfectly clear. Let's start with humidity, which is just a fancy word for water vapor in the air. Water vapor is water in its gas form, and the air can hold more or less of it depending on the temperature. Warm air can hold more water vapor, while cold air can hold less. This is why summer days can feel muggy and tropical, while winter air often feels crisp and dry. It's not just your imagination. There really is less moisture floating around in the cold. Now, when meteorologists talk about humidity, they usually mention two things: absolute humidity and relative humidity. Absolute humidity refers to the actual amount of water vapor in the air, like saying there are 12 g of water per meter. Relative humidity, on the other hand, is a bit more emotional. It's a percentage that compares how much water vapor is in the air to how much the air could hold at that temperature. So if the relative humidity is 100%, the air is completely saturated. It can't hold any more moisture, and condensation is likely. That's when you start to see dew fog or clouds forming. You've probably experienced this yourself on a hot summer day. Even if the air isn't saturated, high relative humidity can make everything feel sticky and sluggish. That's because your sweat doesn't evaporate as easily in humid air, which is your body's natural way of cooling down. In contrast, dry air lets sweat evaporate quickly, leaving you feeling cooler, though possibly more like a desert lizard than a tropical bird. Now, let's talk about clouds. These soft, fluffy sky blankets may look light and airy, but they are actually made up of countless tiny water droplets, or ice crystals depending on the temperature. Each droplet is so small it takes about 1 million of them to make a single raindrop. Despite their delicate appearance, an average cumulus cloud, a big puffy one like you might draw as a child, can weigh hundreds of thousands of pounds. That's right, a cloud can be as heavy as a jumbo jet, just floating up there as if gravity has taken the day off. But how do these clouds form in the first place? It all begins with evaporation. Water from oceans, lakes, rivers, and even moist soil gets heated by the sun and turns into water vapor. That vapor rises into the atmosphere because warm air is less dense and more buoyant than cold air. As the vapor ascends, the air pressure drops and the air expands, which makes it cool down. Cooler air can't hold as much water vapor, so the excess vapor condenses into tiny droplets, or ice crystals clinging to microscopic particles like dust, salt, or pollen. These particles are known as cloud condensation nuclei, tiny seeds that allow water to collect and form visible clouds. Different cloud types form depending on how the air rises and how much moisture is available. If the air rises gently, you get stratus clouds, flat grey, and often responsible for that overcast gloom that feels like it's sitting on your shoulders. When the air rises quickly, it can form cumulus clouds, those fluffy cotton balls of the sky. If conditions are unstable and very moist, those cumulus clouds can grow and grow into towering cumulonimbus clouds, which are the giants of the cloud world and the engines behind thunderstorms. There are many other types of clouds too. Cirrus clouds are high-altitude wisps made mostly of ice crystals. They often look like feathers and can signal an approaching weather front. Lenticular clouds form over mountains and look like flying saucers. The Marty clouds hang down like pouches and often appear during dramatic weather events. There's even a type called Altirumulus castellanus that looks like a row of little turrets marching across the sky. The names might sound like Harry Potter spells, but they're all part of a very real atmospheric lexicon. Now, once a cloud forms, it doesn't necessarily rain right away. A cloud needs to grow droplets big enough to overcome the pull of air resistance and start falling. This happens through a process called coalescence, where droplets bump into each other and merge into larger ones. When they become heavy enough, typically about 2 mm in diameter, they fall to the ground as raindrops. In very cold clouds, the process might involve ice crystals instead, with moisture freezing around them until they become heavy enough to fall as snow. Interestingly, raindrops don't look like teardrops, despite what every cartoon ever might suggest. As they fall, they're shaped more like hamburger buns, flattened on the bottom by air resistance. If a drop gets too big, it can split into smaller droplets on the way down. Now, not all precipitation is liquid. When temperatures are below freezing all the way from the cloud to the ground, you get snow. Snowflakes form when water vapor freezes directly into ice crystals, and their shape depends on temperature and humidity. Some look like needles, others like plates, and the classic six-armed star shapes only form under certain conditions. It's true that no two snowflakes are exactly alike, but that's more of a probability issue than a poetic truth. Given enough snowflakes, and we're talking quintillions over the course of a winter, some of them have to be pretty similar. If the air near the ground is above freezing but the cloud is cold, snow can partially melt into sleet, which then refreezes before hitting the ground. Or you might get freezing rain, which falls as liquid and only freezes upon contact with cold surfaces. That one's especially sneaky and can turn roads and sidewalks into ice rinks in a matter of minutes. Then there's hail, which is not just frozen rain, but something altogether different. Hail forms in strong thunderstorms with powerful updrafts. A small ice pellet forms high in the cloud and gets tossed around by the rising air, collecting layers of supercooled water that freeze on contact. Each time the hailstone gets lifted and dropped again, it gains more icy layers, growing bigger and heavier until it finally becomes too heavy to stay aloft. Hailstones can range from the size of peas to the size of grapefruits, though the latter is thankfully rare. Still, if you ever hear of hail the size of golf balls, it's not just a poetic exaggeration. It happens, and it's best experienced from indoors. Water doesn't always need to fall from the sky to show off. Sometimes it simply condenses on surfaces as dew, those sparkling droplets you might see coating grass on a cool morning. Dew forms when the ground radiates heat overnight and cools down, allowing moisture in the air to condense. If the temperature drops below freezing, the dew turns into frost, which decorates leaves and windows with intricate patterns of ice. All of this moisture movement, evaporation, condensation, precipitation is part of the water cycle, which is nature's endless recycling program. Water evaporates from oceans and lakes, rises into the air, forms clouds, falls as rain or snow, and flows back into rivers and seas to start the journey all over again. This cycle has been running for billions of years and is essential to every form of life on the planet. One more thing, air doesn't have to be completely still for clouds and rain to form. In fact, fronts, boundaries between different air masses, are often responsible for dramatic changes in weather. When a warm, moist air mass meets a cold, dry one, the warm air is forced to rise. This lifting triggers condensation and cloud formation, which often leads to rain. That's why so many weather changes begin with a passing front. So the next time you glance up at the sky and see a cloud, know that it's more than just a floating puff of white, it's the visible tip of an invisible process. A delicate balancing act of temperature, moisture, and motion taking place all around you. Every droplet in the air, every wisp of mist, every sudden shower, they're all part of this vast, elegant water dance happening above our heads, and all of it begins with moisture in the air, unseen, often unnoticed, but endlessly vital. When the atmosphere decides to throw a party, thunderstorms are its version of fireworks. They rumble, flash, pour, and sometimes even toss hail the size of walnuts at your roof. Yet for all their drama, thunderstorms are simply a product of air, water, and a touch of electrical flair, like a weather cocktail with a very loud garnish. Let's begin with how they form. At the heart of every thunderstorm is something very basic. Warm, moist air rising into cooler air above. This rising air is called an updraft, and it's usually set in motion by surface heating. Picture a hot summer afternoon. The sun's been baking the ground all day, and now a pocket of air near the surface gets warmer than the air around it. Because warm air is lighter, it begins to rise. As it ascends, it cools. Remember, air expands and loses heat as it rises into lower pressure. If that air contains enough moisture, it will eventually reach its dew point. The temperature at which the water vapor it carries condenses into liquid droplets. This process releases heat known as latent heat, which gives the air another boost upward. It's like strapping rockets to an already rising balloon. As this continues, a cloud begins to grow. At first, it may just look like an innocent fluffy cumulus cloud, but with enough moisture and instability, it can grow into a towering cumulonimbus, a vertical beast that can stretch up to 10 miles into the sky. That's higher than Mount Everest and then some. Inside the cloud, chaos is brewing. The updraft keeps shoving warm, moist air higher and higher, while gravity pulls the cooled air and falling precipitation down in what's known as a downdraft. This up and down motion is essential, is what drives the engine of a thunderstorm. When the updraft and downdraft become organised and strong, the storm is officially underway. Thunderstorms are classified into 3 stages: the cumulus stage, the mature stage, and the dissipating stage. In the cumulus stage, warm air rises and forms a cloud. It's a bit like blowing up a balloon, steady, controlled, and fairly quiet. Then comes the mature stage, which is when things get noisy. The cloud grows vertically, raindrops start to form and fall, lightning begins to flicker, and thunder makes its debut. This is the stage where updrafts and downdrafts coexist in a swirling dance of moisture and motion. Finally, in the dissipating stage, the downdraft takes over. The falling rain cools the surface, cutting off the warm air supply that was feeding the storm. With no more rising fuel, the storm slowly collapses and fades. But let's not skip over the dramatic centerpiece of any thunderstorm, lightning. Lightning is quite simply nature's way of balancing electrical charges, though it certainly does so with flair. As the storm churns, tiny ice crystals and water droplets inside the cloud bump into each other and become electrically charged. The lighter ice particles tend to pick up positive charges and are carried to the top of the cloud. Heavier hail and water drops become negatively charged and sink to the bottom. This separation of charge creates an enormous voltage difference. Millions of volts between different parts of the cloud, between cloud and ground, or even between clouds. Eventually the air can't resist anymore, and a discharge occurs. That's lightning. The process begins with a step leader, a faint invisible path of charged particles that zigzags downward from the cloud. When it gets close to the ground, the electric field becomes so intense that the ground sends up a streamer to meet it. When they connect, a powerful current surges through the channel, creating a brilliant flash of light. That's what we see as lightning. The air in the lightning channel is heated to around 50,000 degF in just a few micros. That's 5 times hotter than the surface of the sun. The sudden heating causes the air to expand explosively, creating a shock wave that we hear as thunder. Because light travels faster than sound, you always see the lightning before you hear the thunder. If you want to estimate how far away a lightning strike is, you can count the seconds between the flash and the rumble. Divide that number by 5 and you'll have the distance in miles. So if you count 10 seconds between lightning and thunder, the strike was about 2 minutes away. Lightning comes in many flavours. There's cloud-to-ground lightning, which is the most dramatic and dangerous kind, especially if you're holding a golf club in an open field. There's intra-cloud lightning, which dances around inside a single cloud, and there's cloud-to-cloud lightning, which leaps between separate storm clouds, like some kind of atmospheric daredevil. Then there are the more exotic types, ball lightning, which appears as glowing orbs and remains a bit of a mystery, and sprites and blue jets, which are high-altitude electrical phenomena that shoot upward into the mesosphere. Sprites look like red jellyfish and often appear above large thunderstorm systems. They were once dismissed as pilots' hallucinations, but we now know they're very real and quite spectacular. Now, while lightning is stunning, it is also incredibly powerful. A single bolt can carry over 1 billion joules of energy, enough to power a small town for a brief moment. It can cause wildfires, damage buildings, and sadly can be deadly. That's why safety experts say when thunder roars, go indoors. It may not rhyme perfectly, but it's good advice. Thunderstorms also bring another dramatic feature, hail. As mentioned in the previous chapter, hail forms in the strong updrafts of a thunderstorm. Water droplets are carried high into the storm, freeze, and then fall, only to be picked up again and coated with more water that freezes. Each loop adds another layer like a snowball getting rolled across a field. Eventually the Diosos hailstone becomes too heavy for the updraft to hold, and down it comes. Depending on the storm strength, hailstones can be as small as peas or as large as soft balls. And then there's wind. Thunderstorms often produce strong gusty winds as the downdrafts push air toward the ground. These winds can spread out rapidly once they hit the surface. causing what's known as a downburst. Downbursts can be very destructive, sometimes mistaken for tornadoes, though they behave quite differently. Speaking of tornadoes, yes, some thunderstorms do spawn them, but not all thunderstorms are created equal. The ones that produce tornadoes are usually part of a special category called supercells. A supercell is a type of thunderstorm with a rotating updraft known as a mesocyclone. This rotation is caused by wind shear, changes in wind speed and direction with height, which creates a horizontal spinning effect in the atmosphere. If this horizontal spin gets tilted into a vertical orientation by a strong updraft, it can begin rotating around a vertical axis. Inside a supercell, the mesocyon can tighten and intensify. Under the right conditions, a rotating funnel cloud can descend from the base of the storm. If it touches the ground, it becomes a tornado. These events are rare, and the conditions have to be just right, but when they do occur, they're among the most powerful and violent weather phenomena on Earth. Still, most thunderstorms are more modest affairs, short-lived bursts of energy that bring rain, wind, and the occasional bolt from the blue. They can form in clusters known as multi-zell storms or along weather fronts, especially cold fronts, where advancing cool air lifts warm, moist air up into the sky. One interesting phenomenon tied to thunderstorms is the gust front. This is the leading edge of cool air being pushed out by a storm's downdraft. As this air spreads out, it lifts the warm air ahead of it, which can create new storm cells in a chain reaction. In this way, one thunderstorm can give birth to another, like a weather-based game of tag. Despite all the noise and drama, thunderstorms are surprisingly common. At any given moment, there are roughly 2,000 thunderstorms happening on Earth. That's right. While you're lying in bed listening to gentle narration, somewhere on the planet clouds are flashing and grumbling their way across the sky. They're a reminder of how dynamic and alive our atmosphere really is. Each storm is a brief but powerful expression of nature's energy, a temporary disturbance in the atmosphere's endless quest for balance. And when the sky lights up with a sudden flash and follows with a deep rolling growl, it's not just noise, it's the sound of the sky releasing tension, one electric exhale at a time. When the atmosphere really wants to make a statement, when it's had enough of polite breezes and scattered showers, it unleashes its most dramatic spectacles, tornadoes and hurricanes. These mighty tempests are the headline, acts in Earth's meteorological theatre. Swirling masses of raw energy that can carve pith through landscapes and rewrite coastlines. They're loud, powerful, and sometimes terrifying. But beneath the fury, they follow the same fundamental principles that guide all weather, air, moisture, pressure, and motion. Just turned up to 11. Let's begin with tornadoes. Tornadoes are rotating columns of air that stretch from the base of a thunderstorm down to the ground. They're short-lived, compared to hurricanes, often lasting only a few minutes, but they can be astonishingly intense. In fact, they hold the record for the strongest surface winds ever measured on Earth. The most powerful tornadoes can reach speeds over 300 mph. That's faster than a Formula One car and considerably less polite. Tornado formation is still not fully understood, but meteorologists have identified a few key ingredients. First, you need a very strong thunderstorm, usually a supercell, the same kind of storm we touched on in the previous chapter. Supercells are special because they have a rotating updraft called a mesocyclone, which is a spinning column of air within the storm itself. This rotation begins with wind shear, which means that winds at different altitudes are blowing at different speeds or directions. Imagine surface winds coming from the southeast, while higher winds are coming from the west and moving faster. This creates a horizontal rolling motion in the lower atmosphere. If a thunderstorm forms above this zone of rolling air, the storm's powerful updraft can tilt that rotation vertically. The result? A slowly spinning column of air stretching upward through the storm. But not every mesocyclone becomes a tornado. For that to happen, the rotation must tighten and stretch downward, forming a funnel cloud. If that funnel touches the ground, it becomes a tornado. The process is delicate and depends on subtle changes in air pressure, moisture, and terrain. Some storms flirt with tornado formation for hours and never produce one. Others drop a twister with little warning. Once formed, a tornado can travel at speeds ranging from just a few miles an hour to more than 70. Most are small and relatively weak. Classified as EF0 or EF1 on the enhanced Fuji scale, but occasionally a monster emerges. An EF4 or EF5 tornado capable of flattening entire neighborhoods and throwing cars like paperweights. The enhanced Fujita scale ranks tornadoes from 0 to 5 based on the damage they cause. An EF0 might break tree branches and knock over signs. An EF5, the highest rating, tears homes from their foundations and leaves behind a trail of debris that looks more like a war zone than a weather event. Tornadoes are most common in the United States, particularly in a region known as Tornado Alley, which stretches across the Central Plains from Texas up through Oklahoma, Kansas, Nebraska, and parts of South Dakota. The geography here is perfect for tornado formation. Warm, moist air from the Gulf of Mexico meets cold, dry air from the Rockies in Canada, all under a wide open sky. But tornadoes can and do happen elsewhere. They've been recorded on every continent except Antarctica. Waterspouts, tornadoes that form over water, can be found off the coasts of Florida and in the Mediterranean. Even the United Kingdom, not known for its extreme weather, sees several tornadoes each year, though they tend to be mild and rather polite by comparison. Now, let's shift our attention to the larger, longer-lasting and much more predictable cousin of the tornado, the hurricane. Hurricanes, known in different parts of the world as cyclones or typhoons, are massive rotating storm systems that form over warm ocean waters. They can be hundreds of miles wide and last for days or even weeks. While tornadoes are small, violent dancers, hurricanes are enormous, slow-moving engines of atmospheric energy. For a hurricane to form, several conditions must be met. First, you need warm ocean water, at least 70 EGF, extending to a depth of around 150 FOV. This warm water provides the fuel for the storm. Second, you need a pre-existing disturbance in the atmosphere, such as a cluster of thunderstorms. Third, you need low vertical wind shear, meaning the winds at different altitudes aren't varying too dramatically. Too much wind shear can rip a developing storm apart before it gets started. When these ingredients come together, the warm ocean water begins to evaporate, adding moisture to the air. As the moist air rises, it cools and condenses, forming clouds and releasing latent heat. The same sneaky energy release we discussed in thunderstorm formation. This heat warms the air around it, causing it to rise even more. As air continues to rise and spiral inward due to the Coriolis effect, a low-pressure center forms and a tropical depression is born. If the storm continues to intensify, organizing its circulation and drawing in more moisture, it becomes a tropical storm. Once sustained winds reach 74 mph, it earns the title of hurricane. A hurricane has several distinct parts. At the center is the eye, a calm, clear region of a low pressure, where winds are light and the sky may even be blue. Surrounding the eye is the eye wall, a ring of towering thunderstorms that contains the storm's strongest winds and heaviest rain. This is the most dangerous part of the storm. Beyond the eye wall are rain bands, spiraling bands of showers and storms that extend outward for hundreds of miles. Hurricanes are ranked on the Saper-Simpson hurricane wind scale, which classifies them from Category 1 to Category 5 based on sustained wind speeds. A Category 1 hurricane has winds between 74 and 95 mph, enough to cause damage to roofs, trees, and power lines. A Category 5 hurricane with winds exceeding 150 mph can cause catastrophic destruction, rendering areas uninhabitable for weeks or months. But wind isn't the only danger. Hurricanes also bring storm surge, a rise in sea level caused by the storm's winds pushing water toward the shore. Storm surge is often the deadliest aspect of a hurricane, particularly in low-lying coastal areas. Combined with heavy rain, it can cause widespread flooding, sweeping away homes and infrastructure. And then there's the rain. Hurricanes can dump more than 2 ft of rain over just a few days, leading to flash floods and landslides far inland. The size and slow movement of some hurricanes mean that even areas not directly in the path of the eye wall can experience days of torrential rain and strong winds. Interestingly, hurricanes serve an important function in Earth's climate system. They help redistribute heat from the tropics toward the poles, moving excess thermal energy away from the equator. In a strange and violent way, hurricanes are part of the atmosphere's endless quest for balance. Unlike tornadoes, hurricanes are easier to track and predict thanks to satellite monitoring and computer models. Meteorologists can usually provide several days' warning, allowing communities to prepare, evacuate, and hopefully reduce the risk of injury or death. Even so, their sheer size and power make them incredibly difficult to manage once they arrive. And then, just like that, they fade. Once a hurricane moves over cooler water or land, it begins to weaken. Cut off from its warm water fuel source, the storm's engine sputters. Its winds die down and its rains slowly taper off. What remains might be days of cleanup, but meteorologically speaking, the storm has completed its dramatic arc. From a warm sea to a whirling colossus to a rain-soaked memory. Despite their power, both tornadoes and hurricanes are expressions of the same fundamental principles that govern all weather. They're symptoms of imbalance, of heat needing to move, of pressure seeking equilibrium, and in that sense they're not freak events, but entirely natural outcomes of the forces that keep Earth's atmosphere alive and in motion. So the next time you hear a thunderstorm rumbling or see footage of swirling clouds from space, remember these are the Earth's most powerful stories written in air and water. They're turbulent, sometimes terrifying, but also astonishingly beautiful. A reminder of just how alive our sky really is. Wind is the invisible sculptor of our world. You can't see it, but you can feel it dancing through your hair, pushing leaves across sidewalks, and occasionally flipping your umbrella inside out just to remind you who's in charge. It's gentle and wild, playful and destructive, and yet it's really just air on the move, air that refuses to sit still. At its most basic level, wind is caused by differences in air pressure. That's it. When one region has higher atmospheric pressure than another, the air moves from the high-pressure area toward the low-pressure area to balance things out. The greater the difference in pressure, the stronger the wind. It's nature's version of tidying up. Although the results are not always tidy, think of pressure differences like hills and valleys. Air flows downhill from high pressure to low pressure just as water would. But unlike water, air doesn't move in straight lines thanks to the rotation of the Earth. This is where our friend the Coriolis effect comes back into play. As the Earth spins, moving air gets gently nudged, deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This twisting force gives wind its characteristic curves and helps shape the global wind patterns we observe from satellites. Let's start at the planetary scale near the equator where the sun shines most directly. The surface gets heated intensely. Warm air rises, creating a zone of low pressure. That rising air spreads poleward high in the atmosphere, then sinks around 30° north and 30° south latitude, creating high pressure zones there. The air that descends then flows back toward the equator at the surface, creating steady east to west winds known as the trade winds. These trade winds were so reliable that early sailors depended on them to cross the oceans, sometimes to great success and sometimes to unexpected discovery. You could almost say the age of exploration was powered by wind and ambition in equal measure. Between 30 and 60° latitude, the winds blow the other way from west to east. These are the westerlies, and they're responsible for most of the weather systems that move across North America and Europe. Near the poles, we find the polar easterlies, which flow from the east again, bringing frigid air from the Arctic and Antarctic toward the mid-latitudes. All of this is part of the Earth's global circulation system, which breaks the planet into wind belts and jet reams. But wind isn't just a global phenomenon, it's also deeply local. In fact, some of the most fascinating winds occur on small scales shaped by mountains, valleys, and coastlines. Take sea breezes, for example. On a sunny day, land heats up more quickly than water. The warm air above the land rises, creating a low-pressure zone. Cooler air from over the ocean rushes in to replace it, creating a gentle breeze that flows from the sea to the land. At night, the process reverses. The land cools faster than the sea, and now the breeze flows from land to sea. This rhythmic exchange is one of nature's simplest wind patterns and one of its most soothing. In mountainous regions, wind takes on even more dramatic forms. During the day, air near mountain slopes heats up and rises, drawing cooler air up from the valley in what's called an anabatic wind. At night, the air cools and becomes denser, flowing back down into the valley as a katabatic wind. These daily ups and downs can create dramatic temperature swings, and if you live in a mountain town, they're just part of life. Some katabatic winds are famous in their own right. The Mistral in southern France is a cold, dry wind that blows down the Rhône Valley toward the Mediterranean. It can be fierce, sometimes, exceeding 50 métiarbes, and is known for its role in shaping the region's climate, and even influencing local architecture. Many homes are built with small sheltered windows facing away from its path. In California, there are the Santa winds, which blow from the desert toward the coast during certain times of the year. These winds are hot and dry and can exacerbate wildfires by fanning flames and drying out vegetation. Their arrival is often met with a mix of awe and dread, a reminder that wind, for all its elegance, can also be dangerous. One of the most extraordinary wind systems in the world is the Chinook wind, often called a snow eater. Chinooks occur on the eastern slopes of the Rocky Mountains when warm, dry air descends from the mountains into the plains. These winds can cause temperatures to rise dramatically in just a few minutes by as much as 40 degf in less than an hour. Imagine stepping outside into a winter morning only to peel off your coat by lunchtime. It's a bit like nature turning on a giant hairdryer. Wind can also be sneaky. Some gusts are sudden and unexpected, like microbursts, which are powerful downdrafts that occur during thunderstorms. These bursts of wind descend rapidly from the cloud and spread out on the ground, causing damage that can mimic a tornado. Microbursts have been known to knock over trees, damage buildings, and even pose serious hazards to aircraft. And then there are dust devils, mini whirlwinds that form on hot, dry days when the ground heats unevenly. These are not tornadoes, though they look like tiny twirling versions. Dust devils are usually harmless, spinning a column of air and debris just a few feet wide and a few dozen feet high. They're common in deserts and can make for a meme, if slightly mischievous sight. At the other end of the spectrum, we have gales and cyclones, large-scale wind systems associated with intense low-pressure areas. A gale is generally defined as sustained winds of over 39 km/h, strong enough to bend trees and make walking difficult. Cyclones, depending on where they occur and how strong they are, can bring hurricane-force winds, torrential rain, and massive storm surges. But not all winds are violent or even noticeable. Some are persistent background players, like the jet streams high above the Earth's surface. These festoving ribbons of air located around the tropes can steer weather systems and influence everything from airplane flight times to seasonal temperature trends. They travel at speeds of 100 to 200 mph, flowing from west to east and meandering like lazy rivers in the sky. Jet streams form where there are sharp contrasts in temperature, such as the boundary between cold polar air and warmer mid-latitude air. They shift north and south with the seasons, and their strength and position can influence everything from storm tracks to the development of droughts. When a jet stream dips or wobbles unusually, it can trap weather systems in place, leading to extended heat waves, heavy rain, or prolonged cold snaps. Despite being invisible, wind shapes our world in profound ways. It transports moisture, spreads seeds, carries pollen, and even erodes rock into sand over time. It sculpts sand dunes in deserts, and snow drifts in the Arctic. It powers sailboats across oceans and turbines across plains. It's both a gentle whisper and a force of change. Throughout history, humans have both respected and relied on wind. Ancient mariners used it to navigate the globe. Farmers have watched it for signs of changing weather. Today, we harness it for renewable energy, capturing its power to turn giant blades and generate electricity without burning a drop of fuel. Wind also plays a subtle but important role in temperature regulation. It carries warm air away from hot places and brings cool air into warm ones. On a hot day, a breeze can feel like a lifeline. On a cold one, it can bite straight through your coat. This is where the concept of wind chill comes in, a measure of how cold it feels when wind removes heat from your skin. It doesn't actually lower the temperature, but it sure feels like it. And while wind may seem chaotic, it's governed by precise laws of physics. It follows the paths laid out by pressure gradients influenced by topography, temperature, and the spinning Earth. Whether it's a gentle rustling of leaves or the howl of a winter storm, wind is a language the planet speaks every day. So next time you hear the trees swaying outside your window, or feel a breeze graze your cheek, take a moment to appreciate the silent, swirling presence of wind. It's a constant companion, always moving, always reshaping the air around us. And though we can't see it, wind is one of the clearest signs that the atmosphere is alive, in motion, and full of quiet power. When winter arrives, it doesn't tiptoe in quietly. It transforms the world. Trees stand bare and still. Ponds freeze over like polished glass, and the air takes on a bite that nips at your nose. Snow drapes rooftops, softens sound, and paints the landscape in hushed white. But behind this peaceful picture lies a flurry of fascinating science. Snow, ice, sleet, and freezing rain aren't just different kinds of winter weather. They're the icy fingerprints of the atmosphere's coldest moods. Let's begin with snow, the most iconic symbol of winter. A snowflake starts its life high in the atmosphere as a tiny dust particle. Water vapour in the air condenses directly onto this speck and freezes, forming an ice crystal. As the crystal floats through the cloud, more water vapour continues to condense and freeze onto it, causing it to grow. The shape of the snowflake depends on temperature and humidity, which change constantly as the flake falls. That's why no two snowflakes are exactly alike, or at least the chances of finding two identical ones are extremely low. Most snowflakes form the classic six-arm shape, a hexagon. This is because of the molecular structure of water. Each molecule of H2O tends to bond at a specific angle, forming symmetrical repeating patterns. Some flakes look like plates, others like needles or stars. Under a microscope, they reveal breathtaking geometric detail, all sculpted by nothing more than temperature and air moisture. Snow is light, but it adds up fast. A single cubic foot of fresh, fluffy snow can weigh between 5 and 15 lb, depending on moisture content. When millions of flakes fall over an area, it's easy to see how a gentle snowstorm can quickly turn into a heavy burden on rooftops and tree branches. Wet snow with its higher water content is denser and heavier than the dry, powdery kind favoured by skiers. Now, not all frozen precipitation is quite as elegant. Sleet occurs when snowflakes begin to fall from high cold clouds, but pass through a layer of warmer air on the way down. In that warm layer, they partially melt, becoming little droplets. Then, as they descend further and pass into a colder layer close to the ground, they refreeze into tiny pellets of ice before hitting the surface. These pellets bounce when they land and often create a crunchy layer that's slippery underfoot, but still manageable. Freezing rain, however, is a trickier customer. Like sleet, freezing rain begins as snow high in the atmosphere. It melts completely into rain as it falls through a warm layer of air, but then it enters a shallow layer of cold air just above the ground. The air near the surface is below freezing, but the rain doesn't have time to refreeze while it's falling. Instead, it stays liquid, what we call supercooled, until it hits a surface. The moment it touches something like a sidewalk, a car, or tree branch, it freezes instantly, forming a thin, slick coating of ice. This glaze of ice is beautiful in a dangerous kind of way. It can make every twig glisten like crystal, and every road a hazard. Unlike snow, which can be shoveled or ploughed with relative ease, ice clings to everything and makes walking or driving extremely treacherous. Freezing rain is a major cause of power outages in winter as ice adds weight to power lines and tree limbs, often snapping them. Then there's frost, the delicate patterns of ice that form on cold surfaces during calm, clear nights. Frost forms when the surface temperature drops below the dew point, the temperature at which air becomes saturated, and also below freezing. Water vapour in the air skips the liquid phase and deposits directly onto surfaces as solid ice crystals. The result is often a thin white film that coats grass, windows and windshields with delicate feathery shapes. A related but even more dramatic phenomenon is frost, which forms under very specific conditions, clear skies, calm winds, and a moist atmosphere. The ice crystals grow in complex structures like needles or ferns, creating a fairy tale effect across landscapes. Unlike snow, frost doesn't fall from the sky. It grows in place like atmospheric sculpture. In certain conditions, winter can also bring ice fog. This occurs when tiny droplets of supercooled water in the air freeze into minuscule ice crystals near the ground, creating a dense frozen mist. Ice fog is common in extremely cold places like Alaska or northern Canada, where temperatures often fall below 20 degrees F below zero. It gives the air a silvery glow and can reduce visibility dramatically, just like regular fog, only with a sparkling frozen edge. And let's not forget the wind's role in winter. Cold weather often feels colder than the thermometer says thanks to wind chill. This is not an illusion. It's a real measure of how quickly heat is being stripped away from your body by the wind. Your skin naturally warms the thin layer of air around it, creating a tiny thermal buffer. Wind blows this warm layer away, forcing your body to work harder to stay warm. The faster the wind, the faster the heat loss, and the colder it feels. For example, if the temperature is 20 degrees dF, but the wind is blowing at 15 nm, it might feel more like 5 dF. Wind chill doesn't change the actual temperature, but it affects how quickly frostbite or hypothermia can set in. It's a reminder that wind isn't just a summer breeze, it can be a winter bite. Then we have blizzards, the heavy weights of winter storms. A blizzard isn't defined just by snowfall, it's about wind and visibility. According to meteorological standards, a blizzard must have sustained winds or frequent gusts of at least 35 mph, along with visibility reduced to A4 mile or less, all lasting for at least 3 hours. You could technically have a blizzard without new snowfall if a loose snow is being blown around by strong winds. Blizzards can paralyze cities, strand travelers, and cause whiteout conditions that make even short trips incredibly dangerous. Yet for all their force, they often begin with the same basic ingredients as any other storm: moist air, cold temperatures, and atmospheric instability. In contrast, snow squalls are brief, but intense bursts of snow and wind that can appear suddenly and reduce visibility in seconds. They're short-lived, often lasting less than an hour, but they can cause sudden drops in temperature and hazardous driving conditions. If you've ever gone from clear skies to blinding snow in under a minute, chances are you've been caught in a snow squall. While winter weather can certainly be challenging, it's also incredibly important. Snowpack in mountainous regions provides essential fresh water when it melts in the spring. Ice helps regulate the Earth's temperature by reflecting sunlight back into space. Even frost and snow help insulate the soil, protecting plant roots from extreme cold. So the next time you see your breath in the air or catch a snowflake on your glove, remember you're witnessing one of the atmosphere's most complex and delicate performances. Each icy detail, from a frost-tipped leaf to a snow-covered field, is the product of precise, elegant physics, and behind the silence of falling, snow lies a story of temperature, motion, moisture, and time written in flakes and told by the wind. Some weather creeps in quietly. No thunder, no lightning, no dramatic snowstorm. Just a gentle thickening of the air, a soft grey curtain that blurs the world and mutes the morning. This is fog, the most mysterious of weather's children. It doesn't roar or crash, it whispers, swirls, and transforms the familiar into the unknown. And while it may seem simple, fog is full of subtle science and quiet complexity. At its core, fog is nothing more than a cloud at ground level. It forms when water vapour condenses into tiny liquid droplets suspended in the air near the surface. These droplets are so small they don't fall as rain. Instead, they float, scattering light in all directions and limiting visibility. The result? A world that feels closer, quieter, and sometimes a bit dreamlike. There are several kinds of fog, each with its own personality shaped by temperature, humidity, terrain, and time of day. Let's start with the most common type, radiation fog. Radiation fog forms on calm, clear nights when the ground cools rapidly. As the ground loses heat, it chills the air directly above it. If that air is moist and the temperature drops to the dew point, the point at which air becomes saturated with water vapour, condensation occurs. Tiny water droplets form in the air and fog begins to settle. This type of fog often forms in valleys or low-lying areas where cool air collects, and it usually appears in the early morning hours just before sunrise. Radiation fog is delicate. A light breeze can stir it away. As the morning sun warms the ground, the air heats up and the fog slowly evaporates, rising like a curtain being drawn back from the stage. Then there's advection fog, which forms not from nighttime cooling, but from air masses moving across surfaces of different temperatures. Imagine warm, moist air blowing over a cold surface, like a warm sea breeze moving over a chilly coastline. The cold surface cools the moist air, and when it reaches the dew point, fog forms. Advection fog can blanket large areas and last all day if the cooling continues. It's common along coastlines and can stretch for miles, creating that classic seafaring fog you see in old novels and lighthouse movies. UPS slope fog is another variation found in hilly or mountainous terrain. This type forms when moist air is forced to rise up a slope. As the air climbs higher, it cools due to the lower pressure at altitude, and again, if it cools enough to reach its dew point, fog forms. Unlike radiation fog, UPS slope fog can occur during the day or night, and tends to linger until the wind patterns shift. Now for a more unusual guest, evaporation fog, sometimes called steam fog. This fog forms when cold air moves over warmer water. You'll often see it above lakes, rivers, or even hot tubs on chilly mornings. The warm water evaporates into the cold air just above it, increasing the humidity. That Sudden mix of warm moisture and cool air causes immediate condensation, forming wisps of fog that rise and curl like steam from a pot. It's a beautiful sight, ghostly, delicate, and fleeting. One of the most dramatic types is freezing fog. This occurs when the air temperature is below freezing, but the fog droplets remain in a liquid state, what we call supercooled. These tiny droplets can remain liquid even at temperatures well below 32 degrees F. When they come into contact with a surface such as a tree branch, a car mirror, or even a telephone wire, they freeze instantly. The result is a coating of rime ice, a rough milky white layer of ice that can create a surreal frosted world. Unlike frost, which forms directly from water vapour, rime forms from liquid droplets freezing on contact. It can build up quickly and create hazards, especially on roads or aircraft. Still, it can also turn everyday objects into sculptures of ice, each one formed by wind and chill, but not all fog is created equal. Mist is very similar to fog, but by definition, it's less dense. The difference comes down to visibility. If you can see more than 1 kilometre, about 6/10 of a mile, it's mist. If visibility drops below that, it's officially fog. Mist may feel lighter, more like a suggestion than an event, but it's built from the same tiny droplets and forms under similar conditions. Then there's haze, which can look similar to fog from a distance, but is caused by dry particles in the air rather than water droplets. Haze is often the result of dust, smoke, or pollution. It scatters light in a different way than fog, giving the sky a dull, washed-out appearance. Haze doesn't feel damp like fog does, and it doesn't require the same temperature and humidity conditions, but it can still affect visibility, mood, and even breathing. Fog has an interesting effect on sound too. In dense fog, sound waves behave differently. They get scattered and sometimes muffled, making noises seem closer or farther away than they really are. A train horn might sound distant one moment and startlingly close the next. This distortion adds to fog's mysterious feel. It doesn't just blur your vision, it blurs your senses. And of course, fog plays tricks with light. When headlights hit dense fog, the light reflects off the water droplets, bouncing back at the source and creating glare. This is why driving in fog can be so difficult. High beams are almost useless. They just light up the fog itself. That's why fog lights are mounted lower on a car. They aim under the densest part of the fog, improving visibility just enough to see the road ahead. Fog also has cultural and emotional weight. It shows up in poetry and film, in mystery novels and bedtime stories. Fog can feel peaceful or ominous, romantic or eerie. It's a setting, a mood, and a metaphor all rolled into one. It invites you to pause, to listen, to look more closely. It asks you to slow down. But behind all that softness and symbolism is solid science, dew points and condensation, temperature gradients and air movement. Fog may seem like nature's quietest weather, but it has a rich and active life. Next time you wake up to a world wrapped in fog, take a moment. Step outside, feel the dampness on your skin, and watch how the air seems to breathe. Remember that you're standing inside a cloud, one built not in the sky, but right at your feet. It's weather at its most intimate, wrapping around you like a gentle secret, suspended between air and water, between visibility and imagination. Sometimes weather doesn't arrive with drama. There's no thunder, no lightning, no swirling snow. Instead, it creeps in slowly, turning up the temperature degree by degree until everything feels heavy, sluggish, and just a little bit too still. Welcome to the world of heat waves and droughts, where the air hangs thick, the soil cracks, and even the breeze feels like it's been warmed in a toaster. Let's begin with heat waves, those long stretches of unusually hot weather that seem to bake everything in sight. A heat wave isn't just a hot day or two. It's a prolonged period of significantly above average temperatures, often combined with high humidity. The exact definition of heat wave varies depending on where you live, since what counts as extreme heat in London is very different from what's considered normal in Las Vegas. But in general, a heat wave lasts for at least 3 days with temperatures well above the average for that location and time of year. Some heat waves last a week, some stretch into 2. A few can persist even longer, especially if they're reinforced by stagnant high-pressure systems in the atmosphere. So, what causes a heat wave? At the heart of most heat waves is a high-pressure system, often called a ridge when viewed from a weather map. This system acts like a giant atmospheric lid. Air under high pressure is sinking, and as it sinks, it warms. This descending air also suppresses cloud formation, allowing more sunlight to reach the surface. With no clouds to offer shade and no rising air to generate rain, the land bakes. Day after day, the heat builds. In some cases, heat waves are amplified by local geography. In urban areas, the combination of concrete, asphalt, and human activity creates what's called an urban heat island. Cities absorb more heat during the day and release it more slowly at night, keeping temperatures elevated. That's why a summer night in a city can feel uncomfortably warm, even when the countryside nearby cools off. Trees, grass, and open soil help release heat more efficiently, while city blocks hold onto it like a thermal sponge. Humidity plays a key role in how we experience heat. When the air is humid, your body struggles to cool down through sweating. Sweat is your natural air conditioning system. It evaporates from your skin, taking heat with it. But if the air is already saturated with moisture, sweat evaporates more slowly, making you feel hotter than the actual temperature. This is where the heat index comes in. Like wind chill in winter, the heat index is a measure of how hot it feels when humidity is factored in. For example, if the actual temperature is 95 degrees F and the relative humidity is 55%, the heat index might be closer to 110. That's the kind of heat that makes asphalt sticky and makes you seriously question the wisdom of genes. Prolonged exposure to extreme heat isn't just uncomfortable, it can be dangerous. Heat exhaustion, heat stroke are serious health risks, especially for older adults, children, and people with pre-existing conditions. Symptoms include dizziness, rapid heartbeat, nausea, and confusion. During a major heat wave, it's not uncommon for health services to see a spike in emergency calls and hospital visits. This is why cooling centres, shaded parks, and even well-timed fans can make a life-saving difference. Now, let's talk about droughts, the long, slow counterpart to heat waves. While heat waves are loud and immediate, droughts are silent and creeping. A drought is a prolonged period of below-average rainfall that leads to water shortages. It doesn't announce itself with fanfare. It simply begins when the rain stops showing up. Droughts can last weeks, months, or even years. Some build slowly, while others arrive suddenly after a dry winter or a failed rainy season. The effects depend on where they occur, but the consequences are far-reaching. Shrinking rivers, cracked soil, dried-up reservoirs, and stressed crops. In extreme cases, droughts can lead to famine, forest die-offs, and even migration as people are forced to leave areas that can no longer support them. Drought is measured in several ways. Meteorological drought refers to a simple lack of precipitation. Agricultural drought affects soil moisture and crop health. Hydrological drought refers to low water levels in rivers, lakes, and aquifers. And socio-economic drought happens when water shortages begin to affect the economy and society. When cities impose water restrictions, farms can't irrigate, and food prices begin to rise. Several factors can cause or contribute to drought. One is atmospheric circulation patterns like El Niño and La Niña, which can disrupt normal rainfall patterns around the globe. El Niño tends to bring drier conditions to regions like Australia and Southeast Asia, while La Niña can shift the jet stream and reduce rainfall in the southwestern United States. Other factors include persistent high-pressure systems, changes in ocean temperatures, and even long-term climate shifts. Drought is also closely linked to rising global temperatures. As temperatures increase, evaporation rates go up. That means water disappears more quickly from soil, lakes, and vegetation. Even when rainfall does occur, it might not be enough to make up for what's lost to evaporation. In some cases, intense rain following a drought doesn't help much. It simply runs off the hardened soil, unable to soak in, and can even cause flash flooding. The relationship between heat waves and droughts is often circular. Drought dries out the land, which reduces evaporation, which in turn can allow temperatures to climb even higher. With no moisture to absorb the sun's energy, more heat goes directly into warming the air and the ground. It's a feedback loop that can lock regions into long spells of dry, sweltering weather. Despite their challenges, both heat waves and droughts are natural parts of Earth's climate system. They've occurred for millions of years, but in recent decades, their frequency and intensity have increased in many parts of the world. Scientists attribute this trend in part to climate change. A warmer atmosphere holds more energy, which makes extreme events, including heat and drought more likely. Adaptation to these conditions is becoming more important. Cities are investing in green roofs and tree canopies to combat urban heat. Farmers are switching to drought-resistant crops and smarter irrigation techniques. And water conservation is becoming a crucial part of everyday life. In places where rain can no longer be taken for granted, still, there's beauty even in the dry and the hot. A parched landscape reveals patterns in cracked earth. Wind-blown grasses and the silhouettes of trees standing defiant under a harsh sky. Heat waves can turn sunsets into fiery masterpieces as the sun dips low through a shimmering horizon. And when the rain finally returns after a long drought, it's not just weather, it's a homecoming. So the next time the air is still and the heat settles in, take a slow breath. You're witnessing the quieter side of weather. Not the flashing kind, not the rumbling kind, but the kind that reshapes things in silence. Heat and dryness may not make headlines the way storms do, but their effects run deep, carved into soil, memory, and the long story of the atmosphere's endless balancing act. Some weather phenomena dazzle us with sound and fury, roaring winds, pounding rain, or blinding snow. Others, though, choose to enchant rather than overwhelm. They appear in the quiet aftermath of a storm, or when sunlight meets moisture in just the right way. These are the gentle wonders of the atmosphere, the optical illusions and subtle spectacles that remind us the sky's at its heart an artist. Let's start with the most iconic of all, the rainbow. A rainbow isn't an object you can touch or travel to. It's an optical and meteorological phenomenon, essentially a trick of light and perspective. When sunlight passes through a raindrop, it gets bent or refracted, then reflected off the back of the drop and finally bent again as it exits. This bending and bouncing causes the light to split into its component colours: red, orange, yellow, green, blue, indigo, and violet. Each colour bends slightly differently, with red refracting the least, and violet the most. The result is a circle of colour. Although we usually only see a semicircle or an arc, the ground gets in the way of the full shape, unless you're lucky enough to view a rainbow from an airplane or a high mountain where you might glimpse the full circle hanging in mid-air. The angle of a primary rainbow is always about 42 and from the direction opposite the sun. That means the sun has to be behind you and rain or mist has to be in front of you. It also means you can never actually reach the rainbow. It moves with you. You're not seeing the same rainbow as someone a few feet away. Each viewer sees a slightly different version built from the light entering their eyes alone. It's as personal as a fingerprint, but made of light. Sometimes you'll see a double rainbow with a second fainter arc outside the first. This occurs when the light reflects twice inside the raindrop before exiting. Because of the extra reflection, the secondary rainbow appears higher in the sky and has its colours reversed: red on the bottom and violet on top. Between the two arcs, there's often a darker band called Alexander's band, named after the ancient Greek philosopher who first described it. Now, what happens if the sunlight interacts with something other than rain? Enter halos, sundogs, and pillars of light. Atmospheric optics formed not by raindrops but by ice crystals in high-altitude clouds. These crystals are usually found in cross-stratus clouds which form 5 to 8 mm above the Earth's surface. A halo is a bright circle, often with a subtle rainbow edge that forms around the sun or the moon. It happens when sunlight or moonlight passes through hexagon-shaped ice crystals that bend the light at an angle of 20 secondagrund. The result is a ghostly ring that seems to float around the sun like a celestial crown. Halos can appear in any season, but they're especially common in cold weather when the upper atmosphere is rich with ice. Sundogs, also known by their more poetic name Paralia, are bright spots that appear on either side of the sun, often within a halo. They look like small, colourful duplicates of the sun and can be surprisingly vivid, especially when the sun is low in the sky. Like halos, sundogs are caused by ice crystals, but the crystals must be oriented just right, like tiny floating mirrors. Then there are light pillars, vertical beams of light that appear to shoot straight up from the sun or even from street lamps. These are caused by flat plate ice crystals slowly falling through the air and reflecting light in a column. They look otherworldly, like something out of a science fiction film, but they require no aliens, just a calm atmosphere and the right kind of ice. Another lesser-known gem is the glory. Despite its grand name, a glory is delicate and subtle. It appears as a series of coloured rings. much like a miniature rainbow that form around the shadow of your head when it's cast onto a cloud or fog bank. Glories are most often seen from airplanes when the aircraft casts a shadow on a cloud below, surrounded by shimmering rings of colour. The effect is created by scattered sunlight interacting with tiny droplets in the cloud. Pilots and passengers alike often refer to it as the glory of the pilot. Also related are coronas, which form when light diffracts around individual water droplets, creating tight, colourful rings around the sun or moon. Unlike halos, coronas are small and close to the bright object. They're often seen through thin clouds or mist, and have a much more compact pearlescent appearance. And then of course there's the sky's more flamboyant display, crepuscular rays, sometimes called God rays. These are beams of sunlight that appear to radiate from the sun, often during sunrise or sunset when the sun is low and clouds scatter the light. The rays seem to fan out across the sky, but it's really just perspective at work, similar to how railroad tracks appear to converge in the distance. Crepuscular rays are caused by light streaming through gaps in clouds or mountains and illuminating particles in the air, dust, moisture, even pollen. The light and shadow work together to create sharp contrast that our eyes interpret as rays of divine or magical light. Now, let's venture into the twilight for one more optical marvel, the green flash. This rare event occurs just before sunrise or just after sunset when the sun is almost entirely below the horizon. For a second or two, the top edge of the sun can appear green. This happens because the atmosphere acts like a prism bending sunlight. Blue and green light bend more than red and orange, and under the right conditions the last sliver of sunlight may appear green. It's brief. Blink and you'll miss it. But sailors and skywatchers have cherished sightings of the green flash for centuries. There's also lunar rainbows or moonbows, which are exactly what they sound like. Rainbows formed by moonlight instead of sunlight. These are much fainter than regular rainbows because moonlight is so much weaker. You need just the right conditions. A full or nearly full moon, rain or mist in the air, and the moon positioned low in the sky behind you. Moons often appear white or silver, but if you look closely or photograph them with a long exposure, you might spot their pale colours. All of these phenomena are reminders that light and atmosphere are constantly playing together. We don't always notice the show, but when the conditions are right, the sky becomes a canvas for optical marvels, subtle or bold, fleeting or long-lasting. You don't need fancy equipment to see these wonders. Just a bit of curiosity, a willingness to look up, and sometimes the patience to wait for the perfect combination of light, moisture, and timing. Whether it's a rainbow arching after a summer storm, a halo encircling a wintry sun, or a faint glory floating around your airplane shadow, each of these phenomena is a quiet whisper from the sky, reminding us that nature doesn't only work in thunder and lightning, it also speaks in colour, in shimmer, in light, bending gently through air and water. The weather may shape the world, but light paints it, and every now and then the atmosphere becomes not just a system, but a gallery. Weather can be intensely local. You might be enjoying sunshine while your friend a few miles away is sheltering from rain, but it's also wonderfully global. Around the world, weather varies wildly depending on geography, latitude, ocean currents, and even elevation. From sticky monsoons to swirling sandstorms, each region has its own unique climate fingerprint. Let's take a slow and fascinating tour of how weather works around the world and how the same sky can behave so very differently from place to place. Let's begin with the monsoon, one of the most important and dramatic seasonal weather systems on the planet. The word monsoon comes from the Arabic musim, meaning season, and it refers to a seasonal wind pattern that brings a major shift in precipitation. Most people associate monsoons with heavy rain, but a monsoon is really a large-scale wind reversal, driven by temperature differences between land and sea. Nowhere is the monsoon more powerful than in South Asia, particularly India, Bangladesh, Nepal and surrounding countries. In the summer, the land heats up faster than the ocean, creating a large area of low pressure over the Indian subcontinent. Moist air from the Indian Ocean rushes in to fill the void, rising as it hits the Himalayas and condensing into vast columns of rain. The result is weeks or even months of nearly non-stop precipitation. The monsoon is essential to life in the region. It waters crops, fills rivers, and recharges aquifers, but it can also bring dangerous floods, landslides, and disruptions to daily life. Still, it remains a welcome guest to millions, especially after the scorching dry heat of pre-monsoon summer. Further east, places like Thailand, Vietnam, and the Philippines also experience monsoon patterns, though the timing and strength vary. In East Asia, the East Asian monsoon brings hot, wet summers and cold, dry winters, heavily influencing agriculture and urban planning alike. Meanwhile, in northern Australia, a monsoon system brings tropical storms and torrential rain to the top end during the southern hemisphere's summer, usually from December to March. Locals call it the wet, and it's accompanied by stunning lightning displays and dramatic steamy skies. Now, let's take a detour into the world of desert weather, a place where extremes are the norm. Deserts are often thought of as empty, lifeless spaces, but they are teeming with atmospheric action. In Sahara, the world's largest hot desert, daytime temperatures can soar above 120 degrees F, while nighttime temps may plummet by as much as 40 or 50 again. That massive swing is due to the dry air and lack of vegetation. Without moisture to hold heat, the ground quickly radiates warmth back into space once the sun sets. But deserts aren't just about heat. One of their signature features is the dust storm, known in parts of North Africa and the Middle East as a habu. These towering walls of dust are created when cold downdrafts from thunderstorms hit the ground and push dry soil and sand into the air. These walls can stretch for miles, reduce visibility to zero, and sweep across cities like a giant eraser, blotting out the sun and coating everything in a fine layer of grit. In Australia, desert regions experience similar phenomena, sometimes with winds carrying red dust across the entire continent. And in the American Southwest, dust storms are common during late summer when thunderstorm activity peaks. Across the globe at high latitudes, the story changes dramatically. In the Arctic and Antarctic, weather is ruled by ice, wind, and extreme light cycles. Winters bring perpetual darkness and frigid temperatures, while summers are marked by endless daylight and melting permafrost. One of the defining features of polar weather is the katabatic wind, a cold, dense air mass that flows downhill from ice-covered plateaus. In Antarctica, these winds can reach hurricane force, sweeping snow across the frozen landscape in blinding whiteouts. Despite the cold, the polar regions are technically deserts because they receive very little precipitation. Most of the snow there fell thousands of years ago and has simply never melted. When it does snow, it's often in the form of tiny ice crystals drifting gently to the ground, almost too delicate to notice. Now let's head to the tropics, where weather is as vibrant as the landscapes themselves. Tropical regions near the equator, such as the Amazon, Congo Basin, and Southeast Asia, are home to rainforests. Lush environments that receive consistent heavy rainfall year-round. Here, convectional rainfall dominates. The intense solar heating during the day causes warm air to rise rapidly, condensing into towering clouds by afternoon and producing near-daily thunderstorms. These storms are usually short but intense, releasing bursts of rain that nourish some of the most biodiverse ecosystems on Earth. The consistency of the weather in these regions helps create the conditions for dense vegetation, layered canopies, and a constant hum of life. Travel just a bit farther from the equator, and you reach the savanna zones where rainfall is seasonal. Long dry periods are followed by bursts of wet weather, shaping ecosystems where grasses dominate and large grazing animals roam. The timing of rains here is crucial. Too early or too late, and entire food chains are disrupted. Island nations, especially in the Pacific, experience their own unique weather systems. Trade winds, tropical cyclones, and ocean currents all play major roles. The El Niño Southern Oscillation, or ENSO, is one of the most influential global weather patterns. During an El Niño event, warm waters in the Pacific Ocean shift eastward, disrupting rainfall patterns across South America, Australia, Southeast Asia, and even Africa. In contrast, La Niña brings cooler waters and shifts weather, patterns in the opposite direction. Ocean currents such as the Gulf Stream in the Atlantic or the Coroyo current in the Pacific also regulate climate by transporting warm water from the tropics toward the poles. These currents influence coastal temperatures and weather patterns, making places like the United Kingdom much milder than other areas at similar latitudes. In mountainous regions like the Andes, Himalayas or Rockies, elevation plays a key role. As air rises over mountains, it cools and loses moisture. This creates orographic precipitation on the windward side where rain and snow are common. On the leeward side, the so-called rain shadow, the air descends, warms and dries out, leading to arid conditions. This is why places like the Atacama Desert in Chile, just west of the Andes, are among the driest on Earth. In coastal areas, proximity to the ocean can moderate temperature, bringing milder winters and cooler summers. Inland, temperatures tend to swing more dramatically from season to season. That's why Central Asia can experience blazing summer heat and brutal winter cold, while coastal Norway, thanks to the Gulf Stream, enjoys relatively mild winters despite being far to the north. And of course, microclimates add even more variety. A shady ravine can stay cool and moist, while nearby hills bake in the sun. A city block with glass skyscrapers might reflect enough heat to feel several degrees warmer than a nearby park. A vineyard on one slope may produce different grapes than a vineyard just over the ridge. Every region on Earth has its own weather signature shaped by a unique combination of latitude, terrain, ocean proximity, and atmospheric patterns. Yet, despite all this variety, the underlying principles are the same. Heat rises, moisture condenses, air moves from high to low pressure. From the driest desert to the wettest rainforest, the rules are consistent, even if the results are wildly different. So wherever you are, whether you're watching lightning dance across a tropical sky, waiting out a dust storm in the desert, or standing in the still, silent snow of a polar night, you're experiencing one version of the same global story. A story told in wind and water, sunlight and shadow, woven through every corner of the Earth. We've spent a lot of time exploring what weather is, but how do we know what's coming? How can we predict when the next storm will hit, or whether it'll be sunny enough tomorrow to hang out your laundry? Weather forecasting might seem like a mix of science and guesswork, but it's actually a finely tuned art based on physics, data, and a whole lot of careful observation. It's one of the most complex tasks humans regularly attempt, and one of the most helpful. Let's start at the beginning. Observing the present. To predict the future, meteorologists first need to know exactly what's happening right now. And not just in your town or even your country, but across the entire globe. This is because weather is interconnected. A thunderstorm over Texas might be part of a larger system that will eventually influence conditions in New York or even Europe. To gather this information, we use a wide network of tools. At ground level, there are weather stations dotted across the planet. These stations record temperature, humidity, wind speed and direction, barometric pressure, and precipitation. Some are automated, others are monitored by humans. Every few minutes they send their data to central databases where it's used to paint a real-time picture of the atmosphere. Higher up weather balloons, officially called radio sundays, are released from various points around the world, usually twice a day. Each balloon carries a small set of instruments that measure conditions as it rises, reaching altitudes of up to 20 millibars before eventually bursting. These measurements are crucial for understanding the vertical structure of the atmosphere, how temperature, humidity, and wind change with height. That vertical profile helps determine whether the atmosphere is stable, stormy, or somewhere in between. But the real revolution in weather forecasting came with the advent of satellites. Orbiting hundreds or even thousands of miles above the Earth, weather satellites provide continuous images and data from space. There are two main types: geostationary satellites, which stay in one position relative to the Earth and provide constant coverage of the same area, and polar orbiting satellites which sweep from pole to pole, gradually imaging the entire planet. These satellites can see clouds, measure sea surface temperatures, track hurricane formation, and even detect moisture levels in the air. They're also vital for monitoring volcanic ash clouds, wildfires, and snow cover. Many of the images you see on weather reports, those colourful animations showing swirling clouds and approaching fronts, come from satellite data. Radar is another critical tool, especially for short-term forecasts. While satellites provide a bird's-eye view from space, radar systems look out horizontally across the land. A weather radar sends out pulses of radio waves that bounce off precipitation. By measuring the strength and timing of the returning signals, the radar can determine where rain or snow is falling, how heavy it is, and how fast it's moving. Doppler radar, in particular, can detect motion within storm systems, making it invaluable for identifying rotating thunderstorms that might spawn tornadoes. All of this data, billions of data points every day, feeds into numerical weather models. These are computer programs that simulate how the atmosphere behaves based on the laws of physics. They divide the world into a giant three-dimensional grid, with each cell representing a small chunk of the atmosphere. Within each cell, the model calculates how temperature, pressure, moisture, and wind will change over time based on surrounding conditions. The process is incredibly complex. Each weather model runs on powerful supercomputers, churning through equations that represent atmospheric dynamics, thermodynamics, radiation, cloud formation, and more. There are several major weather models in use today, including the GFS, Global Forecast System in the United States, the ECMWF, European Centre for Medium-Range Weather Forecasts, and the UKME TOF. Each model has its own strengths, weaknesses, and areas of focus. Despite the sophistication of these models, forecasts still involve a degree of uncertainty. The atmosphere is what scientists call a chaotic system. Small differences in initial conditions can lead to big changes in outcomes. This is the essence of the so-called butterfly effect. The idea that a butterfly flapping its wings in Brazil could set off a tornado in Texas. It's a poetic way of saying that even tiny measurement errors can grow into large discrepancies over time. To manage this uncertainty, meteorologists use ensemble forecasting. Instead of running a model once, they run it dozens of times with slightly different starting conditions. The result is a range of possible outcomes which can then be averaged or analysed to understand the most likely scenario. If all the model runs agree, the forecast is considered high confidence. If they diverge, it's a sign that the situation is more unpredictable. Forecasts also rely heavily on human expertise. Meteorologists interpret model outputs, compare different models, consider local effects, and apply their knowledge to refine what the computers suggest. A model might not know about the peculiar way a certain mountain range funnels wind or how a particular coastline generates fog. That's where human judgment still plays a vital role. Forecast accuracy has improved dramatically over the past few decades. A 3-day forecast today is roughly as accurate as a 1-day forecast was in the 1980s. 5-day forecasts are pretty reliable, and even 10-day forecasts, while less precise, can give a decent sense of trends. Still, the farther out you go, the blurrier the picture becomes. Tiny uncertainties multiply, and the exact timing or location of events becomes harder to pin down. Short-term forecasts, sometimes called nowcasting, are especially useful for predicting rapidly evolving events, like thunderstorms or tornadoes. These rely on high-resolution radar, local observations, and updated models that run every hour or even more frequently. Meteorologists use this data to issue watches and warnings, helping people stay safe during severe weather. There's also growing interest in probabilistic forecasting. Rather than saying it will rain tomorrow, a forecast might say there is a 70% chance of rain tomorrow. This approach reflects the true nature of the forecast. It's not a guarantee, but a likelihood based on current information. Probabilistic forecasts help people make better decisions, whether that's packing an umbrella or rescheduling a picnic. Beyond predicting tomorrow's weather, forecasting plays a huge role in aviation, shipping, agriculture, emergency management, and energy production. Airlines use forecasts to plan flight routes and avoid turbulence. Farmers depend on rainfall predictions to irrigate crops. Utility companies adjust their systems based on expected heat or cold, and emergency responders use forecasts to prepare for hurricanes, floods, and wildfires. Weather forecasting is also expanding into the world of machine learning and artificial intelligence. These technologies are being used to analyze vast datasets, spot subtle patterns, and improve model accuracy. While they won't replace traditional forecasting anytime soon, they're becoming valuable tools in the meteorologist toolkit. And finally, let's not forget you. That's right. You're part of the forecasting process too. With the rise of smartphones and apps, millions of people now report local weather conditions through crowdsourcing platforms. These observations help fill in gaps between official stations, providing more detailed snapshots of what's happening on the ground. So, the next time you check the forecast and see that it'll be 72 degrees with a 20% chance of showers, remember what went into that little icon. Hundreds of satellites orbiting the Earth, balloons floating miles above the surface, supercomputers solving billions of equations. meteorologists interpreting complex data, and yes, maybe even someone like you standing in their backyard noticing a sudden change in the breeze. It's a staggering collaboration, a global effort to read the sky. And while we can't control the weather, our ability to understand and predict it has never been better. Weather has always been a shapeshifter, sometimes gentle, sometimes fierce, always moving. But over the past century, and especially in the last few decades, we've begun to notice something remarkable. The weather itself is changing, not just from day to day or season to season, but over the long arc of time. And at the heart of this transformation is a force we hear about often, climate change. To understand how climate change is affecting weather, we first need to make a careful distinction between climate and weather. Think of weather as the mood of the atmosphere, what it feels like today or tomorrow. Is it raining? Is it hot? Is there a breeze tugging at your sleeve? Weather is short-term and highly local. Climate, on the other hand, is the personality of the atmosphere. It's the average of all those moods over a long period, typically 30 years or more. Climate tells us what's typical for a place, how much it usually rains in spring, how cold winters tend to be, how often storms roll through. Now, climate has never been perfectly stable. Over Earth's history, it has swung from ice ages to warm interglacial periods. These changes were driven by natural cycles, shifts in Earth's orbit, volcanic activity, solar output, and more. But what we're seeing today is different. The changes are happening faster, and they're being driven primarily by human activity. Since the late 19th century, the average global temperature has risen by more than 2 degrees F. That might not sound like much, but for a system as large and sensitive as Earth's climate, it's a big deal. This warming is largely due to the greenhouse effect, a natural process where certain gases trap heat in the atmosphere, keeping our planet warm enough to support life. The key greenhouse gases are carbon dioxide, methane, nitrous oxide, and water vapor. Of these, carbon dioxide plays the starring role in today's climate story. It's released when we burn fossil fuels like coal, oil, and natural gas. Deforestation adds to the problem by reducing the number of trees that can absorb carbon dioxide from the air. As greenhouse gas concentrations rise, more heat gets trapped in the atmosphere. The result is a warming planet. And that warming doesn't just mean warmer summers, it means changes in weather patterns all around the world. Let's start with heat waves, which we discussed earlier. These periods of intense prolonged heat are becoming more frequent, more severe, and longer lasting. In many regions, heat waves that used to occur once every 20 years now happen every few years or even annually. Urban heat islands amplify this effect, making cities particularly vulnerable. At the same time, nights are warming faster than days. That might seem like a small detail, but it has big implications. Warmer nights offer less relief from daytime heat, increasing stress on the human body and reducing the chance for crops and animals to cool down. Precipitation patterns are shifting too. Some areas are getting wetter while others are drying out. Warmer air holds more moisture, about 4% more for every 100 increase in temperature. That means when it rains, it often rains harder. We're seeing more extreme rainfall events with intense downpours that overwhelm drainage systems, flood streets, and wash away soil. But more moisture in the air doesn't guarantee more rain for everyone. Some regions are becoming drier, especially those already prone to drought. Longer dry spells combined with higher temperatures lead to parched soils, shrinking rivers, and stressed ecosystems. In places like the southwestern United States, southern Europe, and parts of Africa, droughts are becoming more frequent and severe. This pattern, more extremes in both directions, is one of the hallmarks of climate change. Wet areas get wetter, dry areas get drier. It's not a simple warming, it's a reshuffling of the entire system. Storms are also changing. Warmer ocean temperatures provide more energy for tropical storms, which can lead to stronger hurricanes, cyclones, and typhoons. There's evidence that while the total number of storms each year hasn't increased dramatically, the intensity of storms has. We're seeing more Category 4 and Category 5 hurricanes, storms capable of catastrophic damage. These storms also hold more moisture, which means more rainfall when they make landfall. Hurricanes like Harvey in 2017 and Florence in 2018 dumped astonishing amounts of rain, causing widespread flooding even in areas far from the coast. Further north, winter storms are also being affected. A warmer atmosphere doesn't mean we won't have snow. In fact, it can mean more snow in some places because the air can carry more moisture. But the timing and nature of winter weather are changing. Snow seasons are starting later and ending earlier. Snowpack, which acts as natural water storage in mountain regions, is shrinking. Climate change is also altering the jet stream, the high-altitude river of wind that helps guide weather systems across the globe. As the Arctic warms faster than the rest of the planet, a phenomenon known as Arctic amplification, the temperature difference between the poles and the equator weakens. This can slow down the jet stream and make it wobble, leading to unusual weather patterns. A slower wire jet stream can cause weather systems to stall. That means a rainstorm might linger over the same region for days, or a heat wave might lock in place. These stalled systems have been linked to several recent extreme events, from European heat waves to prolonged flooding in the United States. Then there's sea level rise, which isn't weather in itself, but has profound effects on how weather is experienced, especially in coastal areas. As glaciers melt and oceans warm and expand, sea levels are rising by about 8 in since the late 1800s. Higher sea levels mean that storm surges and tidal flooding are more destructive, reaching farther inland and affecting more people. Climate change also influences wildfires, not directly through flames and smoke, but through the conditions that allow them to ignite and spread. Hotter temperatures, drier soils, and earlier snowmelt create longer fire seasons. Lightning strikes, one of nature's ignition sources, may also increase with more convective storms. And once a fire begins, high winds and dry vegetation allow it to spread rapidly. The result is more intense, more frequent, and more damaging wildfires in many parts of the world. From California to Australia to Siberia, these changes don't mean that every weather event is now caused by climate change. Weather will always be variable. There will always be cold snaps, rainy days, and mild seasons. But what scientists can now do is study how climate change increases the likelihood or intensity of specific events. This is called attribution science, and it helps us understand how the background conditions of a warming world are shaping what the atmosphere delivers. So what can be done? First, it's important to recognise that not all change is inevitable. While some warming is already baked in due to past emissions, future outcomes depend on choices we make today. Reducing greenhouse gas emissions, switching to renewable energy sources, improving energy efficiency, protecting forests, and changing how we grow food and use land. All of these can help slow the pace of change. Adaptation is also key. Communities are redesigning infrastructure to handle heavier rains, planting trees to cool cities, and updating building codes to withstand stronger storms. Farmers are experimenting with drought-resistant crops. Cities are mapping flood zones and building seawalls, and individuals, people like you, are learning how to stay safe during extreme heat, conserve water, and reduce their carbon footprint. Even small actions matter. When multiplied across millions of people, those actions become powerful. Walking instead of driving, turning off unused lights, supporting policies that protect the environment. These things add up like raindrops in a storm. The weather is still the weather, capricious, beautiful, unpredictable in its details, but the canvas it paints on is changing. The boundaries have shifted, the stakes have risen, and we are both observers and participants in that change. So the next time the sky darkens unexpectedly, or the summer feels just a bit too long, or the rains come harder than usual, remember you're witnessing not just weather, but a chapter in the larger story of a planet in transition. A story still being written by wind, by water, by people, and still very much within our power to shape. And so we've drifted through the winds and the rains, floated with clouds, and stood in the quiet hush of falling snow. We've explored lightning-lit skies, watched deserts shimmer in silence, and traced the invisible hands that guide our weather from one side of the world to the other. From gentle fog to towering hurricanes, from the science of sunlight to the whispers of wind, we've uncovered just a little of how this beautiful, chaotic, ever-moving system works. Weather is more than just background noise. It's a conversation between earth, ocean, and sky. A language of temperature, moisture, and motion. Written in clouds and spoken in thunder. It shapes the landscapes we live in and the lives we lead. It brings harvests and hardships, calm mornings and wild afternoons, and despite all our instruments and satellites and models, it still finds ways to surprise us. As you close your eyes tonight, tucked in wherever you are, the atmosphere keeps moving. Wind flows silently over mountaintops. raindrops gather on leaves. Somewhere far away, a snowflake is beginning to form. It's comforting in a way to know that the sky never truly sleeps. It simply shifts, reshapes, and continues its slow dance above us. And before we part ways, let me ask again, where in the world are you listening from? What time is it where you are? Midnight to us in the morning, a quiet afternoon with the curtains drawn. Wherever and whenever you are, thank you for being here, for winding down with me and joining this journey through the science of weather. If you found this calming or curious, or just a little bit magical, please consider leaving a like or subscribing to the Calm Cosmos. It helps others find their way here too, and it means a lot. Now, rest well. Let your thoughts drift like clouds, and may your dreams be as soft as fog and as bright as a morning after rain.